Hello guys, welcome again to this video. So in the last video we talked about Poisson distribution and we introduced some of the basic properties of Poisson distribution, right? So just to recall a few, we introduced the Poisson distribution. Random variable x following the Poisson distribution can be written as x following Poisson of lambda, where lambda is the parameter. The PMF was given by probability of x equals to k e to the power minus lambda to the power k by k factorial, where k went from 0, 1, 2 and all the way up to infinity. And we also talked about its expectation or the average value. So it turned out to be lambda itself, which is the parameter, right? We also talked about some parts of calculus like the Taylor series at A for fx. It was just like the following expression, which I shall write again for your convenience. So the function f of x should be differentiable at the point A, and if it is infinitely differentiable and at the point A it is continuous and differentiable both, we can write this as an infinite series of the following form: summation n equals to 0 to infinity f at the nth derivative at the point A divided by n factorial into x minus a whole to the power n, right? Where you can say that 0 less than mod of x minus a less than capital R. Here capital R is what we call the radius of convergence. So this was what we were studying in the last lecture. Of course we also studied the Maclaurin series, but that was just a special case of the Taylor series, like this. So it was just f of x equals to n equals to 0 to infinity, nth derivative at the point 0 by n factorial into x to the power n, right? Okay. Now this gives us all the review, but now, as I already said, we are going to try to explore different parts of the Poisson distribution. We'll be trying to find out how to find different probabilities, how to find higher moments, what could be the moment generating function for this distribution, and also what could be the characteristic function, and lastly the variance, right? So we will do that in order, and we will do which comes first. Firstly, we were trying to investigate about higher moments. So let us see how to do that. Higher moments, right? So what do we mean? What do I mean by moments? See, the moments are basically expectations, or you can say the nth moment. If I define it formally, the nth moment is defined by e of x to the power n. And as I've already said you in the theorem, if you remember Lotus theorem, that is the law of the unconscious statistician, it says that whenever you have a function of an expectation, it basically means you need to sum over all the probabilities or all the values of the random variable like this, and you multiply this random variable with it. So x to the power n into e to the power, it's basically k here, so we can write this as x actually, e to the power minus lambda. Wait, let me just do it clearly in terms of k, because so far we have been doing it in terms of k, so it's better to do in terms of k. K equals to 0 to infinity k to the power n e to the power minus lambda, lambda to the power k by k factorial, right? And this gives you e to the power minus lambda outside, summation k equals to 0 to infinity k to the power n, lambda to the power k by k factorial. Now these things are known as Bell's numbers, b of n, right? These are known as Bell numbers, because they are just an expression for in terms of e, expression in terms of the exponential constant, but we do not really find them in general. So for instance, if you were to find the second one, we can also do that, which I will show you how to do, but we do not really find it generally an expression for the n, but we rather keep it that way. Okay, so let me show you how to find the second moment first. So second moment, and this is also important in order to find the variance, that is why we are going to find out. So e of x square, so the expression for this again would be summation k equals to 0 to infinity k squared e to the power minus lambda, lambda to the power k whole divided by k factorial. Now I'm going to do a bit of manipulations as I go forward with this summation here. What I'm going to do is to change the variables of the summation intuitively. Like in the last example, I had listed you out the whole series, and I made you understand how actually the negative factorials in the denominator cancel out to 0, and thus the whole summation actually changes indices, right? So sometimes from k equals to 0 to infinity means k equals to 2 to infinity, because the first two terms are 0, something like that. So we'll see what. Firstly, we can write this as now. Again, we can write this as follows. Then again, we can do summation k equals to 0 to infinity, and this k minus 1 and 1 can be distributed accordingly, and what we find is two summations, something like this. This should be k minus 1 factorial, sorry. We find something like this: k minus 1 e to the power minus lambda, lambda to the power k divided by k minus 1 factorial plus summation k equals to 0 to infinity e to the power minus lambda, lambda to the power k by k minus 1 factorial. Now as k minus 1 factorial is also k minus 1 into k minus 2 factorial, we can write this as e to the power minus lambda, lambda to the power k, and k minus 1 and k minus 1 cancels off to give you k minus 2 factorial, right? And this would give us the same thing as before. Now after this step, the manipulations, the algebraic manipulations shall start, because we would be trying to express the series in terms of an Maclaurin series of an exponential distribution. So for that we would need to make adjustments, right? So from the first series, take lambda square common, because that would make the power of lambda as k minus 2, which would match the expression in the denominator, and then the series would not matter from where it started. So k equals to 0 to infinity e to the power lambda minus lambda into lambda to the power k minus 2 by k minus 2 whole factorial, right? And this would be k equals to 0 to infinity, and take a lambda common here, e to the power minus lambda into lambda to the power k minus 1 by k minus 1 factorial. Now watching closely, we understand that the series basically starts from minus 2 and it goes up to infinity, isn't it? Because when you put in the value of k equals to 0, it becomes minus 2 factorial here and lambda to the power minus 2. So let's call this series as A and let's call this series as B. I'll try to explain both A and B in a different approach. So let A be this, k equals to 0 to infinity e to the power minus lambda lambda to the power k minus 2 by k minus 2 whole factorial. Expanding, we obviously have e to the power minus lambda common, and inside you can see the series is something like this. And so on. Now obviously, as I have already told you, negative factorials in the denominators means the whole thing is 0, so the first two terms here would be 0, right? And this would just turn out to be e to the power minus lambda into lambda to the power 0 by 0 factorial plus lambda to the power 1 by 1 factorial, and so on. And this would just give you e to the power minus lambda into e to the power lambda, which is 1, because this series is e to the power lambda, right? Because it's the Taylor expansion of e to the power x at the point 0. Now this would give us A, and for B we can see it is basically the same thing, because k equals to 0 to infinity and expanding this, you would see zero by 0 factorial, lambda to the power 1 by 1 factorial, lambda squared by 2 factorial, and so on. So again, the negative denominator, this would mean a 0, and this would give you a total series of e to the power minus lambda into lambda to the power 0 by 0 factorial plus lambda to the power 1 by 1 factorial, and so on. This would give you e to the power minus lambda into e to the power lambda, which is equal to 1, right? So this means that the values of both the series A and B are 1, and thus our second moment could be written as lambda square A plus lambda B, which is basically lambda square plus lambda, right? So this is our second moment. We can in a similar way find the third moment, which I shall show after this, and that would be a bit tricky, but we would try to find the third moment. And once you find the third moment, it would not be a very difficult task for you to find out the fourth, fifth, and anything in between, right? So first let us find the variance using this second moment. The variance is given by, since it's a result, let's do it like this: variance of x is equals to e of x squared minus e of x whole squared, which is lambda square plus lambda minus lambda square, which gives you lambda. So this is the variance of the distribution. and as you can see, the variance and the mean are the same thing here, which basically means a single parameter in the Poisson distribution can define everything that you want to know about the distribution, because mostly it is about the mean and the variance or the standard deviation which you want to know about the distribution, and you do know it here, right? Okay, so this is the variance, so I'll just give a box here because it's very important. And now we shall move to other parts. Specifically we are going to do a difficult task of finding e of x cube, because this is something you would never find in textbooks, and it won't be available much anywhere to find third and fourth moments like that. So it's really hard to do that in like practice. So if it were to come in an examination, or if it were to you have to solve it by yourself, then just solving it once in your life is very important before solving it again, because first try won't be that easy. That is why let us practice this right here, so that next time when you encounter something like the third moment anywhere, you can do that with confidence. Okay, so let us write the third moment down first. The third moment is summation k equals to 0 to infinity k cube e to the power minus lambda to the power k by k factorial. I'm going to explain all of this and what that means as I go along the steps. I'm going to try to fully explain how to find it, as I have done with the first and second moments, but for the time being, let's see. So obviously the first step is to cancel out the first case, which gives us k equals to 0 to infinity k squared e to the power minus lambda to the power k by k minus 1 whole factorial, right? Now k square can be written as follows. So k square can be written as k minus 1 plus 1 whole square, right? And using the formula for a plus b whole square, it becomes k minus 1 whole square plus 2 into k minus 1 plus 1. So we use this to write it as e of x cube equals to summation k equals to 0 to infinity, and we write it here k minus 1 whole squared plus 2 into k minus 1 plus 1 e to the power minus lambda to the power k whole divided by k factorial. So this would give us k equals to 0 to infinity, and we distribute all the terms. So k minus 1 whole square e to the power minus lambda to the power k by k factorial. Sorry, it was k minus 1 factorial actually. Yeah, k minus 1 factorial plus summation k equals to 0 to infinity 2 into k minus 1 into e to the power minus lambda to the power k by k minus 1 factorial, and the third summation would be summation k equals to 0 to infinity e to the power minus lambda to the power k by k minus 1 factorial. So let us name the sums a, b and c. So let this be a plus b plus c, and we would be trying to evaluate a, b, c individually and then add the results of the summation together to find out the answer, right? Okay, first Let's start with A. Okay, so A would be summation of k equals to 0 to infinity k minus 1 whole squared e to the power minus lambda to the power k by k minus 1 whole factorial. Now firstly, one of the k minus 1 could cancel off from up and down, because k minus 1 factorial is essentially k minus 1 into k minus 2 factorial, right? So we can do that, and we can do that as follows: k equals to 0 to infinity k minus 1 into e to the power minus lambda to the power k by k minus 2 factorial. This would give us k equals to 0 to infinity, and we can write this as k minus 2 plus 1, just so, because we again want to cancel a k minus 2, right? Lambda to the power k by k minus 2 factorial, and this would give us again two summations: k equals to 0 to infinity k minus 2 into e to the power minus lambda to the power k by k minus 2 factorial, plus summation k equals to 0 to infinity e to the power minus lambda to the power k by k minus 2 factorial, right? So again, cancelling of the k minus 2, what we get is this: k minus 2 factorial. Now this is a form which we are actually familiar with, but as before, I'm trying to explain this to you in the most elaborate way. So I'll just write the series down in a more expanded fashion. So this basically means e to the power lambda is common for the first one, and we have like lambda to the power 0 by minus 3 factorial plus lambda to the power 1 by minus 2 factorial plus lambda to the power 2 by minus 1 factorial plus lambda cube upon 0 factorial plus lambda to the power 4 upon 1 factorial, and so on, right? And for the second series, plus e to the power minus lambda, we have lambda to the power 0 by minus 2 factorial, lambda to the power 1 by minus 1 factorial plus lambda to the power 2 by 0 factorial plus lambda cube by 1 factorial, and so on. So these are the two series, and now as we know the negative factorials in the denominator, that means that the whole thing is 0, that the fraction whole as a whole is 0. So this would give us e to the power minus lambda into lambda cube by 0 factorial plus lambda to the power 4 by 1 factorial plus lambda to the power 5 by 2 factorial, and so on, right? And the second series would be e to the power minus lambda into lambda to the power 2 by 0 factorial plus lambda to the power 3 by 1 factorial, and so on. If we can take lambda cube common in the first one, what we get is this: lambda cube e to the power minus lambda into lambda to the power 0 by 0 factorial plus lambda to the power 1 by 1 factorial, and so on. And if we take lambda square common in the next one, we get lambda to the power 0 by 0 factorial plus lambda to the power 1 by 1 factorial, and so on. And since we know that this is the Taylor series expansion for e to the power lambda at the point 0, we can write this as lambda cube e to the power minus lambda e to the power lambda plus lambda square e to the power minus lambda e to the power lambda, and this would give us lambda cube plus lambda squared, right? So this is the value for A. So it's quite a long shot, but then again, if you understand each and every step, I think you would be able to do it from scratch again. Let's go with the second one. So for the value of b now, b is given as 2 into k minus 1 e to the power minus lambda, lambda to the power k by k minus 1 factorial, right? This would mean k minus 1 would cancel off and the 2 would be outside. K equals to 0 to infinity e to the power minus lambda, lambda to the power k by k minus 2 whole factorial. And this would also give us 2 e to the power minus lambda. Expanding the series, we get lambda squared by 0 factorial. Actually not that, not lambda squared by 0. It's more like lambda squared upon I need to erase this because it's lambda to it's the reverse actually. It's lambda to the power 0 by minus 2 factorial, because when we put in 0 it's lambda to the power 0 by minus 2 factorial. Then we put in 1, we get this. Then we put in 2 and we get this. For 3 we get 1 factorial and so on, right? So this gives us 2 e to the power minus lambda. Since these two terms are equal to 0 because they have a negative factorial in the denominator, we get lambda squared by 0 factorial plus lambda cube by 1 factorial plus lambda 4 by 2 factorial and so on. And we take lambda squared common to find the series again as before, lambda to the power 0 by 0 factorial, lambda to the power 1 by 1 factorial and so on. As you can see, this series can be reduced very easily, all of this series, but you just need a little bit of manipulations to understand what exactly is going on. So this becomes 2 lambda squared e to the power minus lambda into e to the power lambda. They cancel off and you get 2 lambda squared, which is the value for b. Now let's go back to c, and c looks like a pretty easy one because c is just summation k equals to 0 to infinity e to the power minus lambda, lambda to the power k by k minus 1 factorial, and we can expand this directly as follows. And then again the denominator is a negative factorial, that would be 0, so we are left with this lambda to the power 1 by 0 factorial, lambda squared by 1 factorial, lambda cubed by 2 factorial and so on. And as usual, taking a lambda common would give us lambda to the power 0 by 0 factorial, lambda to the power 1 by 1 factorial, lambda to the power 2 by 2 factorial and so on, which is again exponential of lambda. So lambda e to the power minus lambda e to the power lambda, this gives you lambda, right? So we got the value for all the three series, and now we can finally write that therefore exponential of x cube, the expectation of x cube is a plus b plus c. A was lambda cube plus lambda squared, b was 2 lambda squared and c was lambda. So this gives us lambda cube plus 3 lambda square plus lambda, which is the expectation for x cube, which is in terms of lambda. But as you can see, it's a third degree polynomial, and in general e of x to the power n is let me write it in expanded form. It's an nth degree polynomial like this: lambda to the power n plus a1 lambda to the power n minus 1 plus a2 lambda to the power n minus 2 all the way up to an. So it's a monic polynomial in lambda, but it's not with the like integer coefficient, so it's monic integer polynomial in lambda of degree n So this is what the higher moments look like, and we have also successfully computed e of x cube here. In the next video we shall try to find out the MGF and other properties as well. So I think this is it for this video. Thank you for watching, and do check out Bretter's math app, which is in the link is in the description below, and you can find all the lectures and notes related to this video in that one. Thank you.